Um, so before I start my lecture, let me say that I'm, of course, very, very happy to be here. This is my first visit to San Sebastian. And I find this festival, this science or knowledge festival, absolutely wonderful. And in a way, it makes me feel a bit jealous that we are not organizing similar things in the main French cities, and maybe we will try to do something a bit similar in Strasbourg. So, first, I would like to thank the organizers of this beautiful festival, Pedro, Ricardo, and all the people who participated in the organization. We all know it's a lot of work. This kind of thing, requires a lot of effort, a lot of time from many people. I'm really convinced that you are not all of you, experts in chemistry. And so we will go back in time and maybe go back to the time when you studied chemistry at school, and just some revision about chemistry, and molecular chemistry in particular. So benzene is this. And you see there are several ways of representing benzene, but there is a common feature to these three ways. Benzene is a hexagon. It's a hexagon, and each vertex of this hexagon, here or here, represents a carbon atom. So we do not write carbon anymore. We do not put C anymore. But it's a convention that the hexagon of this type is benzene. There is another molecule on this slide which I like particularly, which is phthalocyanine. Phthalocyanine, it's a little bit more complex than benzene, but to chemists, it's not a very complicated molecule. Maybe it is to you. You see, it has a very nice symmetry. The drawing has a very nice symmetry. It has some kind of axis, symmetry axis here. And it has interesting properties. First, it was made and discovered completely by accident by German industry many, many years ago, more than a century ago. And it turned out to be very useful. So the people used it as a dye. It's a very, very powerful dye. You see powder of this phthalocyanine. You see some stuff which has been colored. You see even some ceramics with phthalocyanine, copper phthalocyanine as the dye. And it's not a marginal molecule, because in Japan, for instance, they produce 10,000 tons a year of this dye. And with 1 gram of such a dye, you can color many, many clothes, a lot of fabric and stuff. Another molecule which was discovered by accident, because accidents are sometimes very happy accidents in science, is C60. C60 is represented like this. And in a way, it's quite simple. It's a soccer ball. The soccer ball has exactly the same numbers of edges and vertices, 60. So if you look here, a classical soccer ball, you will find 60 vertices. And this molecule was really a revolution in many respects. And when the people discovered it, they could hardly believe that it was a nano soccer ball. And the reason why I like this molecule, it's also because it helps us really understand what a nanometer is. We all know that a nanometer is very tiny. Okay, but how tiny is it? And the nanometer, which is the size of this molecule, is very tiny. The ratio between a nanometer and 1 meter, so 1 meter will be here, is roughly the same as the ratio between a small bar, which would be 30 centimeters long, and the distance between the Earth and the Moon. So it gives you an idea. You know, it's really a very, very tiny object. Now, something very important, which will lead to molecular machines. If we take molecules, generally speaking, molecules are static. They are still objects. They may vibrate, they may distort a bit, but we have no control over their movements, over their motions. Now looking at the other family of molecules, biological molecules. In biology, controlled motion is everywhere, and it is absolutely essential. So we will find rotary motors, linear motors, even walkers. There are molecules which walk in biology, molecules which are able to contract or to elongate. And these molecules belong to a very wide class of biological molecules, the motor proteins. They are everywhere. Just 2 examples, but we will mostly focus on one example. ATP synthase is responsible for the making of the biological fuel. ATP, maybe some of you heard of ATP, adenosine triphosphate, is the fuel of life. We use it, we burn it. In fact, we do not burn it, we degrade it in an other way than burning the molecule. And we have to rebuild our stock of ATP every day, all the time. And roughly, we produce 1/2 of our weight of ATP every day. So it's not a minor molecule, you know, tens and tens of kilos every day. And this molecule is made thanks to a beautiful enzyme, which is a rotary motor. So we will not enter the details of the process, but this is the enzyme, ATP synthase. And ATP synthase is kind of embedded in a membrane here. And as ATP is produced, protons, H+, as transported from one side of the membrane to the other side of the membrane. And this proton transfer creates some kind of rotary motion, and this big cylinder rotates. There is an axis here, or a shaft, which is threaded in the hollow part of this big red and green cylinder, so to say. And this motion is responsible for the making of ATP, the purple species, so this is ATP, and it is made from ADP, adenosine diphosphate, in yellow, and inorganic phosphate. It's a very complex system, incredibly complex system, but it works fine. And everything which is living on Earth relies on this enzyme. Basically, we, human beings, have the same enzyme as the most primitive organisms, archaeas, or very primitive bacteria, which appeared on Earth many, many years ago, billions of years ago. Now the question is simple. Can synthetic molecules be set in motion in a similar way as motor proteins? Very ambitious. And we will switch and get closer to chemistry. There is a family of molecules which are called catenanes and rhotaxanes, which have been dreamt of by chemists for many, many years, for even more than a century. So this is a very simple catenane. The word catenane comes from Latin. Catena means chain. In Italian, catena is also chain, and I think in Spanish it should be cadena, which means a chain. So here we have the simplest chain you can think of, 2 cyclic links. It's a catenane. Here you have something similar, but it's not a cycle. It's an axis which has been threaded through the first cycle. So why are these molecules really exciting in relation to motion, to molecular machines? Very simple. If you imagine that you can make a rotaxane of this type, a very simple rotaxane, and if at the same time you are able to set the system in motion in such a way that the red ring here will move to the right and go back to the left, and again to the right and to the left, you are making a linear motor. A linear motor with a molecule, very, very similar to a piston moving in a cylinder. If you are able to spin the red ring about the axis on which it has been threaded, you are on your way to making a rotary motor, and this is also true here. So clearly, these species are very well adapted to rotary motors, linear motors, and generally speaking, to molecular machines. Now I will explain you how we started, how our group started in this field, and I think it could be of interest for the young people in the audience who want to do science. We were working, when I started my group, on a big project which is called photochemical cleavage of water. Photochemical cleavage of water can be a very important project, because if you can cleave the water molecule using solar light, you will generate hydrogen and oxygen. And hydrogen is certainly the very best fuel you can think of, because when you burn it, you do not make CO2, but you just make water. So a lot of research teams have been working in this field, and they continue to work very hard, trying to find very good systems for converting light energy, namely solar energy, to chemical energy. And we had a molecule which was very promising, very interesting in relation to photochemical cleavage of water. And this molecule is represented here. So that was a collaboration with an American friend, David McMillan at Purdue University. And quite simple chemistry. We started from this organic molecule. So again, all the vertices here are carbon atoms. And if we mix this molecule and copper, we generate this species. So I will try to do it with my fingers. We take 2 such fragments, this one, 2 such fragments. At the middle, we have copper, and we do this. Very simple. It works fine. It's done in a few seconds. And we were happy. But then we had an idea. And the idea is quite simple. If you are able to connect this point to this other point, you generate a ring which will be in a vertical plane. And separately, if you can connect this point to this other point here, you make a ring which is in a horizontal plane. And these 2 rings are very special. They are interlocking. You make a catenane. And so we realized, so we have a very nice trick to make a catenane, and catenanes were basically unknown. nobody could make them in a satisfactory fashion. So we embarked in this project trying to make catenanes. And there is a small point which I would like to make. So we jumped from a field which we knew very well to another field which was kind of virgin. For the young people interested in science and who maybe want to do research, the message is clear. Be adventurous. Do not be scared to jump from what you know well to something you know less well, in which you may have some good idea. So after less than 1 year, we had our first catenane. We could make it at relatively large scale, maybe 1 gram within a few weeks. And it was a new life for catenanes, because all of a sudden everybody realized that catenanes are very accessible molecules. And I would like to pay homage to Christiane Dietrich-Büchecker, the lady who was working with me on this project. And she was a fantastic chemist, and it worked thanks to her talent. A small video just to show you how it works. So we start from this. We will mix with copper, and we obtain this N-twine species. And now we cyclize from one point to the other on the other side. So we made 2 rings, and indeed, everybody understands now that the 2 rings are interlocking with one another. Another strategy was a little bit more complex. We made this ring, this cyclic molecule, and there are 2 nitrogen atoms here. We mix with copper, copper jumps in, another fragment inserts itself in the ring, and finally, we make the ring, the second ring, we cyclize. Maybe I will play it again because it's a little bit too fast. So copper, and then a second fragment, organic fragment, and finally we cyclize. So just to tell you, so that was, of course, the first macroscopic synthesis of a catenane, and we became very interested in topology, molecular topology, and we have devoted a lot of time, a lot of effort to making molecules with a strange topology. We are not going to talk about that, but this is just to show you that chemists could make knots. This is the trephine knot. This is the Solomon link, a kind of exciting topology, but this is another field of research. Now let me explain you how we could set the systems in motion. So we start from a catenane. This is a catenane we made, relatively simple, and we have a metal at the center of this molecule. And the metal is copper. Maybe you remember, or maybe you don't, but copper can also be an ion. An ion is a charged species, a salt, so to say, and there are 2 states, copper 1+ and copper 2+. Copper 1+ is red, and the molecules containing copper 1+ are red. And copper 2+ is green, and copper 1+ and copper 2+ have very different properties. Copper 1+ likes to be surrounded by 4 nitrogen atoms, and copper 2+ loves to be surrounded by 5 nitrogen atoms, a big difference. Now the trick is very simple. We start from copper 1+. Copper 1+, for the moment, is very happy. 4 nitrogen atoms, it's a very smiley copper 1. At the back here, we have 3 nitrogen atoms, so they will slowly enter the game. We abstract an electron from copper 1+, and we generate copper 2+, if you abstract an electron. Copper 2+ is terribly unhappy because it is surrounded by 4 nitrogen atoms. So the organic backbone will react, will try to help. The ring, which is here, will glide. The 3 nitrogen atoms originally at the periphery of the molecule will kick out the 2 nitrogen atoms which were here and replace them in the copper-2 center surrounding. So you do a half turn, you generate a new species with a very stable copper-2 center, 5 nitrogen atoms. And you can go back. You go back, you inject an electron, copper-1+, the system is very unstable, and it will rapidly go back to the starting state. I have I think, a nice video, which I will show you. So this is exactly what I described, but probably we see it better with the video. So we abstract an electron from copper-1, we generate copper-2+, the system moves, and now we have a very stable copper-2+. We inject an electron, we destabilize the system, it moves back to the original position, etc., etc., etc. You can do it as many times as you like with the molecule. So that was the first molecular machine we made, and simultaneously, our good friend Fraser Stoddart and his colleagues made a molecular shuttle. Molecular shuttle is simple. You have a ring which glides from the green station, which is here, to the red station and goes back. Of course, you must find some trick to set the system in motion, but I think we have no time to discuss that. So if I refer to this piece of work, it is also because it generated a lot of interest. The people were interested in making memory devices based on molecules. And this molecule, it's very complex. We will not discuss it. But just for you to know that they could write 0 or 1, they could read 0 or 1 with this molecule, and they could erase so that all the molecules were at the 0 state. And it led to an electronic memory device which was very, very dense. The density of information was extremely high. Now let me talk about what we call artificial muscles. So, although this is very pretentious, to remind you, muscles are totally different from springs, metal springs. In metal springs, you introduce some tension in the matter, but not with our muscles. Our muscles are based on filaments which glide along one another. You have thick filaments and thin filaments in red. And when the thin filaments glide towards the center of this little element of a muscle called a sarcomere, the system contracts. So there is a very ugly video, but I think it helps to visualize the system. So if you glide the thin filaments in red, you realize that you contract and maybe you can relax. Well, if you do that, it must be very, very, very tiring, to contract and elongate at this rate. So what we did was making a molecule which is represented in a very schematic fashion on the slide. It is a rotaxane. It's a slightly complex rotaxane. You have a filament here, a light blue filament and a light blue ring, and a deep blue filament threaded through the light blue ring and attached to the dark blue ring. And now the system we know has a total length of 8 nanometers. We send a chemical signal to the system, and it will contract down to 6 nanometers. Another signal, it will go back to 8 nanometers. etc. And that was, as far as I know, the first nanomuscle that chemists could design and prepare. Let me take another example, which is not at all a piece of work done in my group, but this is the work of Ben Feringa and his group in Groningen in the north of the Netherlands, and they made a rotary motor. This slide is very difficult to understand, except if you are really an expert, but something perhaps can be understood. You have a carbon atom here, a carbon atom here, and in between you have two segments, which means that it is a double bond. You have a C double bond C species, and when you shine light, UV light, on a C double bond, it will change shape. And we will go from here to here to here to here, but let's forget about the chemistry. Let's look at the video. They published a beautiful video, which I hope you will be able to visualize. So there will be 4 steps. A thermal step, which is indicated by this symbol, very clear, heating. And then a photochemical step, so a flash of light. The 3rd step will be again thermal, heating. And the 4th step will be photochemical. And you will see that the system will undergo a complete turn. So we heat now. We shine light. We heat. We shine light. So can you see that it's rotating? I'm sure some people can visualize the motion. Yes? Yeah. And I think the video is really spectacular, but the work is even more spectacular. And so they did a lot of work with rotary motors. So this is the first rotary motor. And something which was very popular, which many people liked, maybe 6 years ago, they made a nanocar. So a molecule which is about 1 nanometer long. And this molecule is equipped with 4 wheels. And the 4 wheels are the rotary motors we have just seen. It is deposited on a surface. It can be a metal surface. It's classical, or sometimes graphite. And when you excite the molecule, now it's an electronic process, the molecule moves. I think I'm not going to say that the molecule behaves like a car, going regularly on a highway. It's kind of jumping around, but it moves thanks to the motion of the wheels. And that was, of course, very exciting. A good demonstration that chemists can make objects which have really exciting properties at a very, very, very low level in terms of length. So let me finish up by telling you that many, many examples of molecular machines have been published since 1994, when the 2 first molecular machines were reported. We've seen a pirouetting catenane, a molecular shuttle, a light-driven rotary motor. So this is our work, Fraser Stoddard's work, Ben Feringa's work, so the 3 laureates. Molecular compressor, molecular pumps. Molecules can accumulate, build up energy when they pump. Molecules able to walk on a rail, and this is a beautiful piece of work, like kinesin or dynein in the biological world. So the molecule can walk on a rail, not for very long, 2 or 3 steps, but this is the beginning. Perhaps the most spectacular system is a rhotaxane, very complex rhotaxane, acting as in a similar way as the ribosome being responsible for the making of proteins and peptides, and they could make a tripeptide based on their system. A rhotaxane which is able to flap wings, and there are many, many other systems. So just to conclude, before the emergence of molecular machines, synthetic molecules were mostly considered as still objects undergoing random motion, and let's say the control motion with synthetic molecules, that was basically unknown. And this is what we have brought. I mean, the people working in this field brought a new concept, which is controlling the motion in a very strict way for complex molecular systems, and making rotary motors, linear motors, and all that. Very often I'm asked about applications. I should say that today there is only one commercial application, but we hope that for the future there will be important applications. Activation and catalysis, so towards enzymes. And enzymes are very often kind of biological molecular machines, and we hope that we will be able to make artificial and complex molecular systems which will behave like enzymes, and targeting of tumoral cells. And the previous speaker has given a great lecture also related to that, but using mesoporous nanoparticles. And we believe there is room for several types of approach, molecules and nanoparticles. And there is an additional motivation, which is the fascination that biology exerts on chemists, on molecular chemists. Molecular chemists dream sometimes of designing and making molecular systems which resemble, which are a bit similar to complex biological systems. And I would like also to say that even though there are very few applications today, we have to keep in mind that basic research is very important. Any important technological tool we are using today, or even in medicine, originates at some stage from basic research done 10, 20, 50 years ago. Let me finish up by saying that the work I have described is highly collective. I have been working with a team of people, with permanent people, university professors, and professional researchers, PhD students, postdocs. It's an experimental science, and of course, it is thus a teamwork, and I would like to thank them, all these people. We have no time to name them, but I would like to thank them, as well as my university, the European Commission, my good friend and former mentor, Jean-Marie Lehn, whom I get closer to just maybe 6 or 7 years ago, when the CNRS suggested me to retire, and I was invited by him to join his beautiful institute. And some teachers, my family, and my 2 very good friends, Fraser Stoddart and Ben Feringa. Let me tell you that I know Fraser Stoddart since 1979, so that's 40 years from now.
And Ben Ferringla, we are good friends since 1988. And in Stockholm, when the people there saw us, the three of us laughing, joking together, they were very happy and a bit surprised, because I think it's not so common that three laureates seem to be really very, very close friends. Thank you for your attention. Thank you.